Okay, so this is a video lesson where we are looking at the quantum mechanical model of the atom. And previous to this model, you have really learned the Bohr model of the atom. So that is the idea that the electrons are found in very distinct energy levels orbiting the nucleus, and the energy level that they are located in depends on the amount of energy that they have. Now, when we looked at the quantum mechanics that you looked at previous to this lesson, we started discussing some other ideas about the likelihood of where we would find an electron. So there's the uncertainty principle that says that you cannot know the location and speed of an electron because they just move so fast that it's so unlikely that you can know both of them at the same time. And because the electrons are moving around the nucleus so very, very fast, we have this idea of probability. So the probability model is a model or is a theory that describes the likelihood of where we would find an electron. And the area where we are likely to find an electron is called an orbital. So the orbital is different than an orbit because the orbit is that very distinct shell of electrons around the nucleus. We knew exactly where they were, exactly how much energy that they have. An orbital is the area of probability where we are going to find an electron. And so this brings us to the quantum mechanical model. The quantum mechanical model uses 4 quantum numbers to describe the position of electrons. And it's important to remember that this is still just the likely position of where the electrons are. As I go through this lesson, you're probably going to want to hit pause so you can copy down the information that you see on your screen, because this is going to become your note for quantum mechanical model. And it has been supported by some other videos with other instructors explaining the orbitals of electrons. So when we are describing where the likely position of an electron, we use 4 different numbers. The first number is our principal quantum number. It's represented by n. And this relates to just the distance the electron is from the nucleus. So this describes the main shell we are familiar with. So this describes that idea of the Bohr's orbit. How far away from the nucleus can we find these electrons? So that's principal quantum number n. The second quantum number is L. Excuse me. L are subshells or sublevels of n. And within the principal quantum number, within n, there are different levels of n. So you have to think about it as subshell 2. So when n equals 2, the first or the second distance away from the nucleus we can find our electrons, there is actually a 2.1, a 2.2, a 2.3, a 2.4. And so the number of subshells actually depends on what n is. Because the further away from the nucleus, the more subshells there are that exists. In fact, n can only have 2 different subshells. And so L, which is our sublevel of n, can equal any whole number, 0, 1, 2, 3, all the way up to infinity, all the way up to what the maximum number it can have, is n minus 1. So L can equal any number up to n minus 1. So over here, it shows that if n equals 1, then L can equal 1 minus 1. So the maximum number that L can have when n equals 1 is 0. So if n equals 2, so the second distance from the nucleus, the maximum number L can have is 2 minus 1. So L can equal 0 or 1. So 2 subshells. So this means that there are 2 subshells or 2 types of orbital shapes in subshell or in energy level 2. So energy level 1, when n equals 1, there's only one shape, L equals 0. In energy level 2, there are 2 different shapes of orbitals, 0 or 1, because L describes the shape of the orbital. So we're going to move on and take a look at what those shapes are. So each value of L is identified by a specific letter. So when L equals 0, it's the s orbital. When L equals 1, it's the p orbital. When L equals 2, it's the d orbital. And when L equals 3, f, 4, g. We are only going to look at the shapes for s and p because they get very, very, very complicated once L equals 2, 3, or 4. So when you have n equals 1 and L can equal 0, you have orbital s. And the orbital shape for s right here looks like this, is a sphere. So here's the sphere for 1s. 1 means we're the first distance away from the nucleus. S means is our L shaped orbital, and the L or the s orbital is a sphere. So this is 1s. Now, 2 can also have an s orbital. And so 2's s orbital is actually a much bigger sphere than the 1s. So the important thing to remember is that when L equals 0, it's an s orbital and it has a sphere shape, S for sphere. Now we also talked about above, we mentioned that the 2 energy level 2, principal quantum number 2, can also have an orbital that is 1 because 2 minus 1 is 1. So when L equals 1, it's a p orbital, p right here. And the p is a dumbbell-shaped orbital. So 2 for second distance away from the nucleus, p for the shape of the orbital, L is p shape, which is a dumbbell, and it looks like this. So we have our first 2 quantum numbers, n, distance away from the nucleus, L, shape of the orbital. And remember, we're still just talking about the likelihood of where we would find an electron. So when it is a 2s, the likelihood we would find the electron is in this spherical shape around the nucleus. And we consider, I don't think I mentioned this, but where all the lines meet, we're going to consider to be our nucleus. So that brings us to our third quantum number. And remember, you are pausing this video when you need to copy. So our third quantum number is the magnetic quantum number. And it is the symbol ML right here. What it does is describes the orientation of the orbit in space. Because we have to remember we're dealing with something that's 3-dimensional, and that the orbit can exist on in different angles. And the range it can exist on is from minus L to L. So if L equals 1, then ML can be 1, 0, or minus L. And it's important to remember that if L equals 1, then N had to equal 1, N equaled 2. So these are all within the same distance from the nucleus. So the magnetic quantum number is telling us the orientation or the angle that the orbital is existing in around the nucleus. So when L equals 1, there's 3 orbitals with the same energy. So they have the same N. That's what N is, same amount of energy. They have the same shape. So they have the same L. But they differ by orientation. So they have a different magnetic quantum number, a different ML. And so we look down here and we can say that, if L equals 1, then we have a p orbital. And it's going to be a 2. L equals 1, so they're all p shapes, but they have different orientations. I'm going to talk about those different orientations in the next video.